Thank you.
Please. First speaker is Damiano Anselmi. Since this meeting is devoted to the memory of Alexei Starobinsky, who was one of the founders of this meeting and one of the long-standing organizers, since in the talk of Damiano the word Starobinsky appears in the title, I asked him to open the session with his talk. I'm sorry about this angle, we cannot help yet this problem.
Okay, thank
Better
you.
you stand,
Better
otherwise we
stand.
don't see you.
Okay. So Alexei Starobinsky is also the author of an important prediction about primordial cosmology, and since in the recent years I proposed a theory of quantum gravity, I also inquired what that theory that I will present today predicts about primordial cosmology, and it turns out that the prediction is in agreement with the one that Starobinsky made many years ago in 1980. This is kind of expected actually, because in quantum field theory we have examples of theories that maybe are incomplete, like the Fermi theory of weak interactions, but are nevertheless good approximations of the more complete theory. In that case, it is the standard model. So this is the Starobinsky model. Let me see if I can write here. Yes. So instead of using the pointer, I will write directly on this on the screen. This is the action. You have a correction to the Hilbert term for the gravitational action, and it is just r squared. Or you can convert it into an action where you have the Hilbert term plus a scalar field which interacts with itself and gravity through the so-called Starobinsky potential. And if you study primordial cosmology, you find this prediction by Starobinsky: R is equal to 3 divided by 1000, and that R is the so-called tensor-to-scalar ratio, which means the ratio between the amplitudes of the spectra of the fluctuations of the tensor and scalar fluctuations of primordial cosmology. As you know, the scalar fluctuations have been measured. The tensor fluctuations, the ratio will be measured, they say, in 10 years. And so far we know that this prediction is well within the present bound. But in the case of the Starobinsky model, this is a very sharp prediction. It is one number, there is no error, there is no uncertainty. And in the literature, however, there are all sorts of predictions coming from different models where you study different potentials and double scalar fields and many other variants of this model, or completely different models. And some of those have already been refuted by data, and certainly one of them will be right. But all these models have one problem from the point of view of high energy physics. They are not renormalizable. So you can build all the models you want, but unless you take advantage of the powerful constraints coming from high energy physics, and unless there is a relation between high energy physics and cosmology and quantum gravity, you are basically lost, because this number will be probably only the only measurement data we will have for a long time in this area of physics, high energy physics plus quantum gravity and cosmology. So this is the point. I come from high energy physics. I'm not originally a cosmologist, and I built a theory of quantum gravity that comes from tweaking the basic assumptions of quantum field theory. And it turned out that it is the completion, basically, of the Starobinsky model. So it is this thing here plus a correction, just one correction. And this is what I will present here. So, okay. Again, this is not completely upsetting because the idea is more or less the same as when you have the Fermi theory of weak interaction, which is based on a basic interaction vertex between 4 fermion fields, like the muon decay into an electron and 2 neutrinos. This is the basic interaction. That is a non-renormalizable theory. However, it is accurate anytime you can neglect the corrections due to the intermediate bosons or the Higgs boson. This is modified into that in the standard model, and when you have a standard model, you have a more complete theory that encompasses 3 of the 4 interactions of nature, and it is very, very accurate. And on that we have tons of data that fit with the basic assumptions on which the model has been built, and among those there are locality, renormalizability, unitarity. So unless gravity has some connection with this kind of procedure, you are basically lost. So in quantum, in the market, you can find many proposals of quantum gravity, of course. Don't know if you are familiar with all of them. One can literally get lost. And the problem in those proposals mirrors the problem in the cosmology, primordial cosmology proposals that I mentioned earlier. Namely, you do not have models that can make robust and falsifiable predictions. So I cannot go through all the proposals of quantum gravity. I mentioned just string theory because the people, the supporters of string theories have been claiming that they have a very powerful and sound theory of the universe, but that theory, I think, is fundamentally flawed because a theory that is only on shell cannot, such as string theories, cannot be a viable candidate for the fundamental theory of the universe. And, because when you assume that you are on shell, basically you are assuming a very rough approximation of the description of reality. And quantum field theory does not need that. Quantum field theory is more powerful because you can use, go on shell and build the so-called S-matrix for scattering processes, like the ones we test at CERN, just because you want to. And that's a simplification. So you should be able to work out a framework that's more powerful than these, and at the same time it should be constrained because the theory should be unique. We cannot use data to constrain it, and there will be only one piece of data in the next decade, which is this R. So we'll talk to you a little bit. I will go through the basic idea of quantum field theory that lead to this proposal for quantum gravity. It is based on the concept of purely virtual particle that I introduced some years ago, and that is a particle that can never be observed. So it's a fake particle in the sense that it is always off shell. What does that mean? It basically means that you have it, it's like some intermediate mediator, as you have in the standard model, but which will never be able to be observable in itself. In the standard model, you have intermediate bosons, but have been observed indirectly, actually, not directly, but they have been observed. So you, in case of quantum gravity, you need something similar to the upgrade from the Fermi theory of weak interactions to the standard model, but with some new concept. Otherwise, as you well know, the quantum gravity theories proposed on the market fail. And
so why do you need necessarily a virtual particle?
Yeah, we will come to that, because the point is that you need to solve the problem of renormalizability in this model, and there is a very simple way to do it, which is adding a correction here, which is the square of the Weil tensor, but that breaks unitarity. And so if you copy what has been done for the standard model, you would have something like this thing here, but in the middle you would need a ghost, a -1 particle. So you need to get rid of this dangerous -1. And the prediction that comes out from Primordial cosmology is just this one. It's a small window, less than 1 order of magnitude, and in 10 years probably we will be unable to distinguish what's inside here from the Starobinsky prediction. And so we conclude that basically Starobinsky was right. So as far as today there are 3 different formulations we have developed of this concept of purely virtual particle. I will go through the third one, the latest, because it's more clear. There are some formal things, but the concept is very, very simple. Basically, you have to violate time ordering. You have to violate the idea that you can distinguish present, past, and future for arbitrarily small intervals of time. So this is a diagrammatic formulation because in quantum field theory we use Feynman diagrams. In cosmology maybe also, but we don't need the technology to that extent. Probably are familiar with in correlation functions. In primordial cosmology, that's what you need to make the prediction of R. But in high energy physics, we use the simplest concept of diagram that can be defined, which is Feynman diagrams. You build diagrams with vertices and propagators. But there are many other diagrams that you can study, and the amplitudes for processes are collected into so-called S matrix, and the S matrix is a unitary matrix, and that's important because that's unitarity. The great the advantage of these things in quantum field theory is that everything can be expressed in terms of diagrams. Everything, even this identity, can be expressed in terms of diagrams. And so it's interesting to study all the possible diagrams you can conceive to see what can come out of those. Let me briefly mention how these diagrams are built. These are called Katkowski-Weltman diagrams, and they are made of 2 parts. One divided by a cut, and the cut is the separation between S dagger and S. And on one side you have a normal Feynman diagram. On the other side you have the conjugate of it, and in between you have something very important, which are called cut propagators. When a propagator is cut in 2, it is kind of special because you see it is what connects S dagger and S, and that is a product. It's not a time-ordered product as you have in Feynman diagrams. And that's the crucial difference. A product is as simple as a product. So I will tell you about all the diagrams you can construct in a moment, because in that there will be the answer of something that has been missed basically for many decades. And all the diagrams you can construct are basically functions of S, built as products, or S times S times S. You don't need S dagger actually, because S dagger can be seen itself as a function of S. It is 1 divided by S, so to speak. So the most general diagrams you can construct in quantum field theory are functions of the Feynman diagrams, basically. And the product, S cross S, is something you know to build, because it's another propagator that's commonly used already. So basically you can build diagrams as you normally do with Feynman rules, propagators and vertices, but you add one ingredient, which are cut propagators. As many as you wish. You can have S times S times S times S, and you can sum all the powers of S. And what's in between? These cut propagators are very, very crucial. So again, they are used for in correlation functions, so-called in primordial cosmology, but very general. These are just on-shell, completely, purely on-shell.
Why do you call this thing a propagator, since it satisfies an equation with 0 second?
Exactly, it's a cut propagator. So it's only the on-shell part with the theta function to tell you where.
It's the 2-point function. It's the
yes,
y
exactly.
function.
It is the 2-point function, phi without the time ordering. So it's the product of the 2 fields. And what is the main property of this? That it is purely on-shell. So I'm using this, which is purely on-shell. By subtraction, I will define something that's purely off-shell. That's it. I want to extract the purely off on-shell contents of a particle, which will be the ghost. I'll have to do it inside diagrams because I have to be sure that I get rid of that particle completely, not just among the in and out states of my scattering, but also inside the diagrams, because inside diagrams you have that particle on shell as well, normally. And so, first of all, you have to study all the possibilities, all the diagrams you can build with these ingredients, which are all the functions of S. And just to give you a glimpse of what happens is that when you have, for example, three propagators connected by a dot, unique vertex, you can cut them in several different ways, one, two, three cuts, and instead of one diagram, which is a simple tree diagram, you have 20. But they are all very simple because all these cut propagators are simpler than the full Feynman propagators. So this is kind of something that a computer can do very easily. And these calculations of the diagrams I will define anew can be done with no difficulty. And the triangle diagram will have some cut versions, but every cut version is simpler than the uncut version because these propagators inside are simpler. So once you do that, you sum on all possibilities. That gives all the correlation functions you can think of, and then you look for a magic combination that extracts the on-shell part from particles everywhere, inside the diagrams as well as outside. And the key thing, as I told you, is that this new ingredient, which is purely on-shell, can be used to define purely off-shell particles by subtracting all the would-be on-shell contributions. There is a magical subtraction formula, and we'll describe it in 2 minutes and then move to the most important things, which are quantum gravity and the predictions. And so let me tell you about how unitarity is used normally, is studied. You separate the trivial contribution 1 from the interesting amplitudes, and then you have some identity like this, which I will separate in a different way to have no eyes around. So you have an identity like this with 1 here in a non-sick theory, but normally you can have sick theories like the one that's candidate for quantum gravity, where instead of 1 here, you will have a diagonal matrix with +1s and -1s, which are the bad degrees of freedom, the ghosts. So if you are able to subtract every on-shell contribution of these objects, you define new objects that are purely virtual, and then you have a chance.
So, sorry, can you explain what is again the difference between ghost theory and non-ghost theory?
So in the non-ghost theory, you have this identity as dagger S equal 1, which means that the S matrix is unitary. When you have ghosts, which are fields with kinetic terms multiplied by -1, this -1 reflects into this identity. Fortunately, you have an identity. That's the good point, which is called pseudo-unitarity equation. Mm-hmm. But it is not this one. You have a matrix C in between S dagger and S. And this matrix C is diagonal with some +1s, some -1s.
So you mean when you have a ghost, instead of this relation, you have S dagger CS?
Yes,
equals
it's a
1.
pseudo-unitarity relation, which you can expand in this way.
Okay.
But fortunately, you have a diagrammatic relation because having the possibility of studying these things through diagrams is very, very convenient. So a theory with ghosts is mathematically well defined. Mathematically, you have many, many ingredients, and that's why we can use it to get to the right theory by projecting out the bad part in a way that I will tell you. Because basically now, I will tell you that I start from an amplitude V, I will call it amplitude, that satisfies the wrong identity, and I will look for a function of V that satisfies the right identity. And there is always an answer. And so basically, you take your bad matrix C, and you get rid of all the -1s, and insert zeros in their places. You can get rid of some +1s as well, if you want to get rid of some physical particles. That's something arbitrary so far. And you define a matrix with only pluses and zeros, and B, which will be the difference. And then the question is, can I find a function of the previous amplitude which satisfies a modified identity where in between I do not have minus signs? And that is the answer. There is a magic formula for that, which is an expansion in powers of these matrices and a new arbitrary matrix that you can insert. And then you go on and inspect what possibilities you have. You will see that there is only one that fulfills all the requirements we have in general for Feynman diagrams. And that one does the job and extracts every on-shell contribution of some particle that you want to get rid of.
Sorry again.
Yes.
So this yellow requirement, you say, is a consequence of unitarity condition?
No, this is just an exercise of matrices. I'm telling you that if I have a matrix that satisfies this, I can find a function of V, which I call V reduced, that satisfies that.
But that the first one, the previous one, was because of unitarity or not?
No, this one is a diagrammatic identity satisfied by any theory.
Ah, okay.
And that is pseudo-unitarity. That C with minus ones is the violation of unitarity.
So this V plus V dagger equals something is just a general thing for
Yeah.
any theory, ghost or non-ghost.
For ghost or non-ghost, you will find that the imaginary part from, for example, of this diagram, which is this diagram plus the conjugate, is equal to some.
But it follows from S dagger CS equals 1, right?
Yeah, but that is not an assumption. You have to prove S dagger CS equal 1.
Okay.
That is, even this one is not an assumption in quantum field theory. You have to prove that your theory satisfies that.
I see.
And if a theory has negative kinetic terms, it doesn't. It satisfies another one.
Okay.
So don't take this as an assumption. This is the key point. We have to get to a theory of quantum gravity that satisfies that. This is not an assumption in the standard model or in any theory. It has to be proved. And unfortunately, you cannot do it for all the proposals. For any proposal in quantum gravity, you cannot do it. And but in this way, you can. So you have this new S matrix. You can build now with this new matrix. You can build a new S matrix. Basically, you take this A as a projector, and you project out the wrong part of your field.
But how do you know that in projecting this way you don't break Lorentz invariance and like this?
Yeah. This is built in the formula because it's the new S matrix is a function of the old S matrix. So if the old S matrix satisfies gauge invariance and Lorentz invariance, the new S matrix will do. This is a combination of diagrams, Feynman diagrams, which satisfy, plus diagrams with this propagation, which also satisfy. And so basically, you sandwich your reduced amplitude in between projectors, and the new S matrix will be, instead of 1 plus the amplitude, it will be the projector.
So this is a perturbative
Absolutely,
affirmation,
yeah.
because
Thank you.
if you do this in quantum electrodynamics, you know that when you build charge states, they are not Lorentz invariant.
Absolutely. So let me stress this. What I'm doing here is perturbative. Everything is perturbative. So I want to build a theory of quantum gravity that's perturbative. As QED is, as the standard model is, I have no claim or no ambition to go beyond the perturbative expansion. And I am happy with a theory that works from low energies, gravity, classical gravity, up to the Planck scale, and even QED at some point breaks down, because it doesn't break down. It's the perturbative formulation will have some limits, because even at the standard model, you don't know what the ultraviolet limit of the standard model is, because it is in the non-perturbative region.
But I was talking about the infrared part.
The infrared part here is okay, because it tends to gravity. Plus some corrections, actually. But anyway, the final point of this formal part, and I close, is that the projected S matrix will satisfy this, the identity that you want. So what to do? Let me give you some examples. For example, this is the Feynman propagator. If you collect the diagrams predicted by the formula, you will get rid of its own shell part, and you just have the principal value as, not as a propagator. You cannot use this inside diagrams. You have to use the magic formula I told you. If you study the bubble diagram, for example, this, and you do some extra diagrams in a certain way with a certain coefficient, then you will have the corrected bubble diagram where you will have some principal value inside the diagram, and so on and so forth. You will have a definite answer for all diagrams. So you basically change the notion of diagrams so that outside you will have never ghosts, and inside those ghosts will not be regenerated because you are taking out their own shell contributions even inside the diagrams by defining new diagrams. Basically, this is the idea. Very diagrammatic, very high energy physics. Now, the point is that when you do this, you change also the classical theory, and that is relevant for cosmology. So, basically, let me give you already the example of quantum gravity. In quantum gravity, this will be the idea, the theory. The Starobinsky model, cosmological constant you can ignore for cosmology, primordial cosmology, and this is the correction, the square of the Weyl tensor. So instead of propagating 2 degrees of freedom as in the Starobinsky model, one is the graviton and one is the inflaton, which is the scalar built in R squared, you have a third particle which has spin 2 and mass, some mass, which is the coefficient here. Okay? And you need to treat this, and you will find that if you do normal Farman diagrammatics, this origins a minus sign in the pseudo-unitarity equation. And then you do this projection, which gets rid of it. And basically it is as in the Fermi theory of weak interactions, where you have intermediate bosons. And here the intermediate boson is this intermediate particle. And the point is that you have to do it classically as well, because classically this will not be the right classical action. I call it interim classical action. And so classically you will have the Starobinsky model plus certain fluctuations that you obtain by taking this action here and integrating out with the rules I gave you the intermediate boson. And this corrects primordial cosmology. And this corrects the prediction of the Starobinsky model. And this corrects the prediction for the tensor-to-scalar ratio R. So basically this is the idea. And I have 10 minutes, right?
More than 10 minutes.
It's 14 total?
The talks are 55 minutes up to
55, okay, so...
plus 5 minutes of discussion. If
okay.
you want to use less, you use less.
35 or 55?
35.
35.
35. 35, okay. So basically, the classical theory is obtained by collecting the 3 diagrams. The classical limit of your theory of quantum gravity, in this case, is obtained collecting the 3 diagrams. And the 3 diagrams are those where you have external physical particles and internal purely virtual particles with this propagator now, because we are only at the 3 level. I give you a very, very simple example because it's a prototype that has been studied in the past by Lee and Vick many years ago when they wanted a finite QED. And so they used QED with an electron, but they added a massive Broca field with the wrong sign in front of the kinetic term. This way you can improve the ultraviolet behavior, and the theory of QED, instead of being renormalizable, it becomes finite. And then the problem was how to treat this object which has a negative sign, violates unitarity, it's a ghost, etc., etc. Well, in their approach, if you integrate it out, you have a classical limit where you have this 4 fermion vertex, with the Feynman prescriptions. It's not the Feynman one, it's the opposite of the Feynman prescription. But basically, they have these ghosts have a width. They decay, basically, like muons. And in their paper, they said they were happy having no stable abnormal particles left in the asymptotic states. So that was their idea. In this case, instead of having ghosts which are still there and decay, which is not satisfactory to me, the idea is to have something that doesn't need to decay to be never never on shell, because it's always off shell in between. So you have at all energies. So you have a 4 fermion vertex of this type, where you have in between a certain complicated non-local object. What is this object? Here it is. Just to imagine. So you have to imagine that even in classical physics we have corrections that we do not see, that are parameterized by this very strongly oscillating function, which is a sine, the principal value of this, which is a sine of some frequency, let's say the mass, let's say p equals 0, omega is the mass. And when the mass is very, very large, this non-local thing, basically it's acting even in this moment, but this non-local thing averages to 0 and gets a local 4 Fermi vertex or local vertex. If the mass is very large, so the question is, what is this mass? And this mass is, in the case of theory of quantum gravity I have, 10 to the 13 GeV. And this is similar to the mass of the Starobinsky scalar field, which is 10 to the 13 GeV as per measurements from Primordial Cosmology. So if you translate this in time, 1 divided by m, which is the scale at which you could see these non-localities, this is 10 to the minus 36 seconds. 10 to the minus 36 seconds. I don't know if you are familiar with the most accurate measurement of time today. It is 10 to the minus 18 seconds. So we do not know what time is today by measurements below 10 to the minus 18 seconds. And this is 10 to the minus 36 seconds.
They have improved recently with the nuclear
Probably.
nuclear oscillator.
But 10 to the minus 18 was already optimistic, because it was 10 to the minus 17. Well, anyway, what I want to say is you have this extra particle, you have to do this machinery, now you have to do it in a curved background. The novelty with respect to high energy physics is that in cosmology you have to study the Friedman, Robinson, Walker, the A of t background. You do it, you will have that a complicated green function in between that doesn't look like anything like this. That is the one you have in flat space. But fortunately, in the two basic limits, it becomes something like that. In the sub-horizon and super-horizon limits, in conformal time in one case, in cosmological time in the other case.
So, sorry, how technically do you do this? You have a classical FRW background, and on top of that you have a gravitons, massive gravitons, which you want to integrate out with your method. And the scalar, Starobinsky scalar, right, which are in a perturbative way, right?
Yeah, exactly. Okay. So that's the usual approach, with the only addition that now I have to integrate this out, so I find its green function in the curved background. And then I study it, and I check that in the super horizon and sub-horizon limits, it becomes what I expect, which is an oscillator of constant frequency, but only if I put a bound on the mass of this particle. So this is the crucial requirement that makes the prediction meaningful, because this green function is a sine, you see, of a modulus, but it contains this thing which could be imaginary, and a hyperbolic sign would be unacceptable. So if this bound is violated, I would have an intermediate boson that makes it impossible to build a universe where you have the formation of local structures, like stars or so on and so forth.
Will you comment later on the justification for considering flat space all the way to the Planck scale, which you said you were going to?
Yes.
Because the R-square corrections that will not make it flat space, which are already in the action,
Yes.
are going to be problematic in that regard.
So everything here is perturbative. Now it is perturbative not actually around flat space, but around the Friedmann-Lemaitre.
Yes.
And that will be correct up to the Planck scale. So the reason why this is still meaningful is that it is a very high energies, 10 to the 13, GeV 14, but still below the Planck scale. And this is the prediction coming from this bound. And you have a window now because you have an extra parameter, which is the mass of this new object. But fortunately, since the mass has to satisfy this bound, you have this prediction. So the Starobinsky prediction was that this number will have to be equal to that. NS is the tilt of the scalar spectrum, which has already been measured.
But the 10 to the 13 came from normalizing to the amplitude of the actual derivative by t. So it's a phenomenological input by hand.
Yes, exactly.
In principle, it could have been higher.
Yeah.
In which case, you'd have a problem, but currently you
Yeah.
don't.
Yes. And even this bound is a phenomenological bound because it's there only to make this universe possible.
You live in a perturbative universe with 10 to the minus 5 fluctuations.
Yeah.
If they were of order 1, then it would have an issue.
But I'm not terribly lucky, because if you inspect the formula for these, you will see that basically this window is basically all basically the prediction is just there. So the Starobinsky prediction is confirmed. I will tell you in a moment. Before I just show you for fun that once you have a theory, you can compute basically everything, and you can compute the perturbative, the spectra of the primordial fluctuations as expansion of a slow roll parameter. So here instead of slow roll parameter, I introduce some running coupling in the language of high energy physics. Anyway, from data, this is m phi is the mass from the scalar spectrum, which is this. Alpha is like a fine structure constant of inflation. It is 1 divided by 115, which makes everything very perturbative, fortunately. Everything is normalized with respect to pivot scale, I think it's called. K is the momentum of the spectra. These are the calculations you can do in the Starobinsky model, and then you can compute the corrections in the full theory. And fortunately, you will see that you can compute to high orders in this expansion of in powers of alpha, which is the curved background, basically, without encountering many invasive changes due to the non-localities intrinsic in this integrating out. But from some point onwards, here, for example, for the scalar spectrum, I had to use a perturbative expansion and stop there because they start kicking in. And you can have predictions for the next centuries about the running coupling, the running of the spectra, and so on and so forth. So let me tell you the price you pay when you buy this theory of quantum gravity. You have unitarity, you have renormalizability. So adding c squared, I forgot to mention, improves the ultraviolet behavior. And
so what you call quantum gravity is this theory with R plus R square plus
c squared treated this way.
Okay.
And it's unique in the sense that this, like the standard model, is the unique, strictly renormalizable theory you can build in ultraviolet. So it is renormalizable, it is unitary. What is the price to pay at high energies, which means larger than the mass of this purely water particle, m chi, 10 to the 13 GeV? You cannot speak of temporal ordering, because the diagrammatic is based on non-time ordered products. You cannot make a distinction between past, present, and future. You have some fluctuations oscillating around that.
Which is somehow expected in a theory of quantum gravity or not?
Yeah, but many people expect that at the Planck scale. Here I expect that 7 orders of magnitude below the Planck scale. And it is parameterized by this new thing. And there are other consequences, but this is the basic one. Some people say that this is a violation of microcausality. I avoid using this terminology because causality is a very delicate notion in quantum field theory already. So, but if you want, we can discuss it later. And my time is?
The time is 4 minutes.
Okay. So just a final comparison. If you don't know if you are familiar with how gauge theories are quantized. In gauge theories, you have ghosts also, which are called Faddeev-Popov ghosts, which you need to keep your formulation local. It's very, very convenient diagrammatically because in a gauge theory, if you solve a gauge condition, you introduce non-localities. And so the game here is similar. Basically, you have an extra terms in your action, but you want to get rid of them in the physics, as you do in gauge theories, because in gauge theories you do not consider scattering processes of physics where there are ghosts, Faddeev-Popov ghosts in and out. And you are sure that they are not generated inside the diagrams. So unitarity there is a bonus for free because you have the gauge symmetry protecting you, and that's just how it works. Here you don't have it. So the idea was to show that it is possible to project something out, but since then unitarity is not for free, you have to change the notion of diagrams to have those ghosts not reappear inside. And then I can tell you that this can be generalized to off-shell physics just to make sure that you do not get into something like string theory, which is bound to on-shell physics, which I consider very unsatisfactory. So, to conclude, the prediction arising from the Starobinsky model is in essential agreement with the one that arises from this theory of quantum gravity. The correction is parameterized by this number, zeta, which is 1 divided by 1 plus m phi square to m chi square. So you have this ratio between these two masses, and you know already that m chi by the bound has to be bigger than m phi divided by 4. So unless I am extremely, extremely, extremely lucky, and m chi is close to this bound, this correction will be basically 1.
I'm sorry.
Up to 1%.
Chi is the field which is not observable.
Yes, chi is the
How
extra.
could you measure its mass?
By the fact that even if it is not observable, it mediates, it changes everything.
So you can determine a precise value of the mass of something which is not observable?
Yes, exactly, because it impacts everything else.
So in some sense it's observable.
Like but not as an asymptotic state.
Okay, that's another question.
So it's like, for example, the Z boson and the W bosons have never been observed. But in principle you could, because you can observe even an unstable particle, like the muon. The muon is unstable and you can observe it. But the Z boson and the W boson have never been...
Unstable and non-observable are two
totally different things.
That's
the key.
We don't know this.
The key behind this is that chi is never on shell. It's a purely off shell, but it impacts everything, every prediction. Unfortunately, as I point out, the impact on this correction to the Starobinsky prediction is small, too small to be appreciated in 10 years or so, as long as m chi is already 10 times m phi. So there is room for m chi being 10, 100, 1000 times. In all cases, the correction will be basically 1 and will not be measurable for, I don't know, a couple of centuries. So I have to cross my fingers in 10 years and hope that this will be really, really close to the bound. Thank you.
So there are 5 minutes for more questions if you want.
Yeah, so thank you for the talk. That's very interesting. So you started by comparing to the 4 fermion vertex and saying if you require unitarity at high energy, then you have to open this up and include the mediating boson. And this is similar in that you want to require unitarity at high energy, and you include this massive spin 2 that is always off shell. So comparing to the gauge theory approach, but Tooft and later Donahue kind of popularized this, where you include the Faddeev Popov ghost for the spin 2 graviton, which is always the virtual, the non-physical particle. Does this give you some advantage over that, where in this case your massive spin 2 is always off shell anyway? Is this more reasonable than...
So you are referring to the approach by?
So I'm referring to the approach of quantizing GR as an effective field theory below the Planck scale, and in that case, so popularized more recently by Donahue, but this kind of thing was done by Tooft and Veltman in the 60s too. But in that case, you have to include the Faddeev Popov ghost, just like the like QCD.
That's a spin 1.
In yeah.
Yeah, you have to do that all the time in gravity, but that is not chi mu. This is a spin 2.
Exactly. In this case, you have the massive spin 2, but it's always off shell.
It's always off shell thanks to the new diagrammatics, because you cannot get rid of that as you do with the Faddeev Popov ghost, which is already disappearing because of asymmetry. So you have it is protected by the symmetry. Then there is another approach. I'm not sure if you are referring to that by Donahue, which has this, which is more Liebig style, where this chi mu is there. It is a ghost with, but not a ghost, probably it's better to call it Liebig ghost. Anyway, that is an approach where you have an awkward particle that could be on shell, but it decays. And so you say that it is not in the asymptotic states because it has a width and it decays. In this approach, I don't care if it has a width or not, because I remove it completely from the theory. And that's the key thing, because I do not find an approach satisfactory unless it does this. So I'm not satisfied with saying that you are doing just on-shell physics, and you say that in the spectrum, the muon is what? It's not there in your spectrum. Technically, the muon is not on-shell, but you see the muon. So you need a physics that is able to describe that as well. Because the muon cannot be on shell because it decays, and if it were on shell, it would have an energy. And to measure the energy, it takes an infinite amount of time unless you violate the uncertainty delta T, delta E equal 1. And you can do that only for stable particles. So stable particles are asymptotic, and unstable particles are not. But the fact that you observe the muon tells you that physics cannot be just an S matrix as you normally mean. I'm not sure if... so all approaches Liebig-like, I started this by studying those approaches actually, because I wanted to refute them. And then I turned into this...
But the width of the muon is very small. I mean, what you say is true of, say, the top core. It's non-coderivative, so it's very hard to define it as a on-shell. But muon is pretty sharp. So
yeah, but you're talking practically. I understand that.
Okay,
I want to build a fundamental theory, because I will never get to this prediction of Modern Cosmology otherwise.
I agree.
And that's what my criticism to all the other proposals. They can be good for many phenomenological purposes or effective theories and so on and so forth, but they will lack this key prediction. And indeed, they don't have it.
It's just that experimentalists will get nervous if you say you can't observe muons.
No, I say I can observe muons.
But not as asymptotic states, you're correct.
But, and even if I don't have time here to say it, I restudy quantum field theory in a finite interval of time, and I can show you how the muon
Emerges.
can be explained by the theory. But if we do it as people normally do, experimentalists or phenomenologists, that's self-contradictory. I can show you that there is a contradiction there. Because it assumes that you can observe something, that you are violating the uncertainty relation delta E, delta T
Indeed.
equal to 1.